Welcome to this talk. I gave a version of this talk last year. This is kind of the shorter version of the talk because I ran out of time real fast. So we'll have till 30 minutes?
At least.
So 30, 45 minutes, and I'm going to take you through building Atari 2600. My name is Matt Christensen. I run a software group doing enterprise for a job. Game programming is a hobby of mine. I've fallen down a kind of 8-bit computing console rabbit hole along the way. The side of it, I was doing ham radio, so there's kind of like a whole tech overlap there. And also very clearly, I am not an expert. This is just stuff I like. I'm not a professional developer. I don't have an electrical engineering degree. This is all stuff I've picked up over the years. Which is say if you're like, Matt, that's wrong. Feel free to tell me. What we're going to do today is just write a short 2600 program that shows the 8-bit workshop IDE, which is a free online IDE for building all sorts of 6502 and other retro stuff. You'll learn a little assembly language, and you'll learn how to draw background colors, playfields, and sprites on the 2600. I have, for those of you with laptops, I have a USB key that you can copy code onto if you want to try a long. Some people have it. This is all on GitHub, and feel free to mess around. I'll show you what the final product is here. This is something just to keep things as simple as possible. One of the things with any kind of assembly program, especially on these old hardware, is things get complicated fast because of limitations. So this is designed as a simple proof of concept as opposed to something particularly amazing. I did really annoy Chris earlier, so it's at least successful with that. This is a sincere warning. If you have any epilepsy or seizure disorders, there's blinking in this, so just let me know. You can always turn it off, but it is pretty intense blinking. Okay, so for those of you who are not into retro stuff or under, yes. If you're on the younger side, you may have seen a 2600. There's one right here. This is the Woody model. This is the Darth Vader model. They also have a smaller model that I have. It was popular. Released in 1977, cost $200 at the time, which was like about $840 now. Adjusted for inflation. It only had 9 games. In 1980, Space Invaders released for it. Massive hit. Sold 2 million of them. $2 billion in revenue that year. 1982, they had 10 million total sales, sold $7 million of Pac-Man, which I have is the worst port we've ever played. So it's total garbage. I encourage you to come play it. Then in 1983, there was this thing called Video Game Crash. If you haven't heard of, look it up. It was really kind of a fascinating time. But basically, there was an oversale of this stuff, and just everything fell apart. It made it all the way to 1992 with 30 million units sold. And if you were a kid or alive at all during like the late 70s and early 80s, like people had these. They were like the NES or like the PlayStation became later. Just people would have them, not like enthusiasts, just like random people. Their dad would buy it and like sit and play combat, just over here, like over at their house. Okay. So what's the architecture? So the MOS 6507, which is a variant of the 6502 chip running at 1.19 megahertz. The 6502, you probably recognize it. It's one of the most famous chips ever made. It was also in like the NES, the C64. I haven't listed them later, but it was an incredibly successful chip. It was partially successful because it's cheap. It was like one of the first cheap chips. It has 128 bytes of RAM. Bytes. And I have something later I'm going to show just to see that. 4 kilobytes is wrong. People realize that you can use bank switching to get more ROM. When I say ROM, that's these cartridges. You can do tricks to get more out of it. But 4 kilobytes. The NTSC version was 128 colors, 60 frames per second, so that's right. 60 frames a second, better than certain modern consoles. And a resolution of roughly 160 times 192. If you play Pac-Man, that resolution is why it's weird, because the aspect ratio of the pixels is like 16 by 5 or something, so part of the look of the 2600 is really weird, elongated look. It has a custom chip in it, the TIA. Basically, you have your CPU, you have the cartridge, and like again, if you're not familiar with this kind of hardware stuff, the cartridge was just literally a memory chip that had the game on it. And the 2600 was not actually the first cartridge-based console. That was the Fairchild F, which was never a successful game out of Japan. It was not the first home game console. That was this thing called Magnavox Odyssey. But the games there you play by changing plastic overlays on your screen. All it did was put a dot on the screen. And then there was Home Palm, which was massively popular and what funded and inspired building the 2600. So you had a CPU, you had your cartridge, you had a television interface adapter, that's what hooks up to your TV. And then you have your RAM and you have a few other things like the switches. So it's an extremely simple architecture. I mentioned the 128 bytes earlier, right? So this was my description of the spot over here. So over on the right, that's 128 bytes of 8-bit text. So you cannot even fit the entire description of this in ASCII in 128 bytes, okay? Here's another way of looking at it. If you used 8-bit color, this is what you could do for a frame buffer. I don't mean like this is the actual frame buffer. You could fit like 11 by 11 or whatever. So if you wanted to draw pixels on the screen, if you wanted to store a bitmap image, 11 by 11 is the best you can do, and then you are completely out of memory. There's nothing else for any other part of your game. Okay, so why is it such a piece of garbage? Well, it was to make it as expensive as possible. This was like under 200, I mean, that's the big deal. $840 in the 70s. This stuff was kind of new. That's a lot of money to ask people to pay. And this is before like the home computer revolution really took off. I think, comparison is the Apple II cost almost $5,500 by modern standards. So this was a steal. 8K of RAM back at the time cost $125. So more than half the price of the console, it would have cost more than half the existing price of the console just to put that much RAM in it. The reason they used the 6507 instead of the 6502 is because the 6502 was being sold at $25, and like, that's too much, we need to spend $12 per unit. And so MOS Computing actually went and made a special chip where they took the 6502 and chopped off a whole bunch of the pins, so it can only address 10 bits, which means that it can't even address, like a proper 6502, I think addresses like 32 or 64 kilobytes of memory, but they just chopped it off, so that's why you only have 4K, because to save money, they literally chop pins and addresses off the chip. No one else ever used the 6502 except Atari. I'm sorry, the 6507. So, what are some famous Atari games? Well, you have Combat, which is up here, which is a really quite fun game, and part of the reason they sold it is because it was sold in like one of those, like, we've got 100 games in it or something, where each of the games is this weird variant of a game where you shoot each other. Battlezone, this is kind of an impressive sort of 3D thing. Pitfall, this is probably the best Atari game in terms of just design, and uses a whole procedural generation thing to be able to generate all these levels. It's really a masterpiece. And of course, E.T., which in retrospect is not as bad a game as everyone said. People didn't understand it. But this was also the game that kind of signaled the end of the Atari era. This is a rhythm game I'm working on in the 8-bit workshop IDE we're doing. So, after all that, why? So, there are some bad reasons. One, you have a game idea. What do I mean by that? When you're working with a console like this, the limitations of the console affect the game you can make. An idea is completely worthless because you're just only going to be able to do certain things. You want to be rich, you're not going to get rich making these games. Like, you can sell carts, there's an active homebrew community, I have some, but it's not massive. Or I want to be famous. I mean, you could be like, if you want to be big fish, small pond, I guess you could be famous. But like, most people are just going to look at you weird. So, good reasons. Game preservation and archaeology. If you're just interested in classic games or classic hardware, it's really interesting that you can buy this device made 40 years ago, hook it up to an old TV, and still use it. I love that side of things. The technical challenge is one of the most interesting parts. It is hard to write games for this. It is really, really hard. And if you're on the coding side of things in particular, that kind of challenge is interesting compared to the kind of challenges you have now. It's not like writing a 3D Unity game is easy, but it's a different kind of hard than writing something in assembly to the constraints here. The game design challenge. It's really hard to make a fun game with these limitations. Like, a lot of these games are trash, but I was talking with Mark and Dale earlier, like, you play combat, like, anyone could come up here and we could play and we could have a good 5 minutes. It's fun. It's not Overwatch, but it is a fun game. The joy of constraints. You know, you put the constraints on things, it's like a game jam. You have all these constraints, it makes making things interesting. Like the rhythm game I'm working on, right? Well, a rhythm game in and of itself, there's a million of them, that's not hard. Doing a rhythm game in these contexts, that is interesting. This is my favorite. You can understand the entire stack. If you work with modern software in any way, especially something hooking up to the network, I mean, you're basically casting magic spells to God. It's just stuff happens, and you have no idea. When you do this kind of stuff, and especially if you take a course like from NAND to Tetris, which is like a Coursera course that lets you understand, this is a clockwork machine. This is a watch, and you can understand every bit of it, from how the chip is working to how the stuff is going into your TV, and you start realizing all these things that seem weird, like what an NTSC signal is. It's not weird, it's just that it makes sense when you learn the hardware and the constraints and how things work. So that is, and I find that most fascinating, because you read the stories of like Steve Wozniak or something from the early days of computing. These are guys who are like, you know, men and women who are sitting around without the internet, figuring this stuff out, mapping chips in their head and on paper. But it's a machine, and I love getting back to that aspect. Again, I was joking with Mark earlier, you can develop without obsessing on monetization. Like we were talking earlier, Quasi. You're not going to get rich doing this, so there's no dream that this thing you build is going to be, I don't know, I keep saying Overwatch, the next Overwatch. Like, there's nothing out of it. It's just a hobby. It's something you're doing for fun. And 80s nostalgia, let's be real. It was a decade, I was there, good times. And I think there's actually, like, if you were a young nerd in the 80s, these are the things you admired. Oh, wow, assembly language. Oh, wow, you know, making a cartridge. These are things you couldn't do because you didn't work at a game company or didn't have access. It's really neat to be able to do that stuff. All right, so now we're going to get working. So what you're going to want to do if you're playing along on your computer, so go to 8bitworkshop.com. I'm not affiliated with this website anyway. It's just a cool site. There's a GitHub with this code. I also have it's also on the USB drive if anyone else wants it. And so we're using 8-Bit Workshop. If you get into this, there's an emulator called Stella, which is probably the best Atari emulator, has debugger stuff. And you can use a standard assembler like DASM and just make files and stuff to, if you want a more robust tool chain. But even when I mess around, I like this web UI because you can just see the changes happen. All right, so exercise 0, the Bill's blue background. So what you're going to want to do is, and I'll talk through this and then I'll do it on the computer so everyone can see. Open up 8bitworkshop.com. I'll just go over this. So we'll go over here.
Is there a line that makes
Yeah.
I make games.
I make games.
When is their Discord notifications on? It's really good.
What's that?
Oh, someone's Discord is notifications.
It could be mine. I gave up trying to kill the damn thing. What a terrible project.
It is.
It's just the worst. Okay, so coming in here, so what you're going to do is, if you haven't done this already, you go to this menu, you choose consoles, choose Atari 2600, you can see all the other things you can build with this. Then you do new project on this menu, and you'll call it AtariWorkshop.asm. You can call it whatever you want. And then over in GitHub, so there is, for each of these exercises, there's a starting point. So we're going to go to exercise 0. That's why I'm on the raw here. And you just copy it over to your code here. And you'll see we have a box. So obviously there's a lot of boilerplate here. You need it, like you genuinely need it to set things up. But it's really not that important. So finally what you're going to do is, where it says insert code below this and above this, you're going to type LDA pound $80 and then STA call UBK. So, there you have it. Build. So, anyone working along have any questions? You got that? Hey, every journey starts with setting the background color. Okay, so let's talk about a few things there. So for those of you who are not coders, when you work at this level, when you work with assembly, or even things like C or lower level languages, you have to know the difference between binary, hex, and decimal. Decimal is obviously base 10, what you're used to. In this assembler, that's just a pound sign. So that's just saying this is a number versus number decimal 129. The reason you have to actually put the number sign there is if you don't put the number sign there, it's going to interpret it as an address. So actually a point in memory. So this is saying this is the number 129, not the thing that is memory 129. Although, what's at the memory 129 in this case? We only have 128 bytes of RAM. So the next one there is hexadecimal, hex. So the dollar sign makes it hex, and then you see 8 and 1. Hexadecimal, just the digits are 0 to F. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, which count from 0 to 60. And then finally, we have binary, which are 1s and 0s. So in a 6502, in this kind of system, a byte is 8 bits, so 8 zeros are 1. That breaks up into 2 groups of 4 that, yes, they're called nibbles for real. And each of those nibbles, because it's maps to numbers 0 to 15, maps neatly onto hexadecimal. So you've probably seen hexadecimal at some point in your career, even if it's just like colors in CSS on the web or something. The reason you use hexadecimal is because it maps to nibbles. And when you do this a lot, you see A1, and you know that that's what it looks like. And the other strange thing as you start doing assembly is what it looks like starts to matter. Because a lot of times you're using these numbers as like sprites. Like, okay, this is actually like, dot, no dot, no dot, blah, blah, blah. Or masks, where you're trying to say, okay, I want the first and the last name on things. This is not something you're going to master here. At the same time, it's just numbers. So when you start using this stuff, you figure it out. Like my daughter, Victoria, some of you know, I've been at the gyms. I taught her how to do this like at the diner. It's not hard. It's just something you have to learn. Okay, so going back to the background color, the frame buffer was too expensive. We talked about that. So the 2600 has no frame buffer. There is no way to write pixels to the screen directly. It just doesn't work that way. So instead, the chip in there called the TIA, what it does is you flip registers, and registers are essentially special parts of the memory or the chip that you can control that control various behaviors. So when I went back to that game design point, part of what I was pointing out there is you're writing a game and you literally cannot write a pixel to the screen. You can trick the thing into kind of doing it, but there's no draw at 0, 0. It just isn't possible. Let's see if I had. hate this trackpad. So, going to memory, we talked a bit about memory. Now, I said that you only had 128 bytes of RAM, right? Well, the addressable space is bigger because basically it puts together a virtual memory space from 0 to FFFF. And so the first 0 to 7F there, those are all the TI registers. So when you said over here, star call UBK is just a mnemonic. You call it in, it's a mnemonic for one of those addresses. And that address is actually something on the chip in here, the TIA, that says this is the color to output to the background. The PIA RAM, that's the RAM I was talking about earlier. Then you have some stuff with ports and timers, so like all the switches. And then finally you have your cartridge ROM. But one of the interesting things, if you work with any modern system, is you're kind of used to variables and things being broken up. But in this kind of system, you just have this giant pool of memory, and you have numbers that point to all those bits and pieces, and you just say basically, I want that thing at that address, or I want to put something in the thing at that address. All right, going back to what we wrote here. So LDA over here stands for load to accumulator. STA says store from accumulator. So what we're saying here is load the hexadecimal number 80 into the accumulator, then take the contents of the accumulator and put it into the memory address pointed to by call UBK, the background color. Now, if you have done any programming, you're kind of used to just saying x equals 10, right? But in 6502 assembly in particular, and a lot of assembly language, you can't just move things, modern chips are way different, but back then you can't just say, take this thing and put it in this memory address. You have to move it to one of these registers. And the 6502 has an A register, which is the accumulator, an X register, and a Y register, all of which behave slightly differently. But basically means going to things being more difficult. If you want to set a variable, you have to put the thing in this intermediate thing first, then stick it somewhere else. That's how little hand-holding assembly machine language does for you. Also, quite obviously, there's one variable type, which is byte, and it goes from 0 to 255. There's something called binary coded decimal, which we'll get into. Okay, now things get exciting. We're going to do a cycling background color. Okay, so let's go over and grab exercise 1. Copy that over. And then, we'll let people type first. We'll do STX call to BK, which you'll remember, and then DEX. Okay, I should have also said one of the things that is cool about assembly language is like if you have, you're the kind of nerd who likes the idea of like magic and spells and stuff, like to be honest, like arcane syntax is kind of appealing. Like it's kind of cool being, set background color to blue is boring. This is cool. So we're going to do STX, call you BK, and DEX. So, okay, beautiful. All right, so what the hell's going on there? So, let's talk a bit about, let's try and improve this. So, you can kind of just start where we are. You don't have to copy it over. After the DEX here, go in and type STA WSync. Look how it changed. So what's going on there? Okay, so this is where Atari programming gets really nuts. So this is what an NTSC frame looks like. NTSC is the American version of color TV or black and white TV. PAL is Europe, and then France has CPM for some reason. basically the way when you have a CRT like this, you probably know, but there's an electron beam in here. That's why this thing's so big. And it's going from that side of the screen over to here. Now it has to move back. So how does it do that without drawing? Well, the beam shuts off. It goes back, turns back on, draws, keeps doing that. Now, because you don't know how big the TVs are actually going to be physically, and you don't want to be firing the electron beam at the plastic on the top or something, the NTSC starts with this vertical blank. And so there are 37 lines of vertical blank. And what that means is the electron beam is moved to the top, the beam is turned off, but then it still cycles down for 30 lines. Then on the left, you have this horizontal blank, which is hard to read. I think it's 65 cycles. Then you have the picture. So once it gets there, now your beam turns on, it's drawing, it's rastering. You need to overscan. That's the opposite of the underscan. It's the opposite of the top scan. That's when you're at the bottom of the TV, you turn it off. So the crazy thing about writing for the Atari is the only time your code is running, your code is running at the same sequence, at the same timing as this screen. So if you want to, you have these lines up here to do any code you want. You have these lines down here to do any code you want. And then you have this small space before it starts drawing. But if you start drawing and you make changes to these registers, those changes go live. And it's called racing the beam. Like that. There's a really good Atari book on that, which is say when you're writing for one of these systems, all of your code has to fit within this sequence, because if you're doing the wrong thing at the wrong time, it's just drawing. So going back to what I said about pixels, the way you make more sophisticated games is by carefully timing everything so various things are turned on and off at the right places. So what's going on back here is the W-sync, it's called strobing a register. Strobing just says, okay, if you read or write that register, the system knows to do something. And the W-sync register says, okay, I'm done drawing, wait until I get back to the other side of the sequence. So when this is off, the reason this is a mess is because it's just moving to the edge of the screen, going down and going all the way to the bottom. Because it's not sequenced in any way with the actual line sequence of the TV, it's changing at a different rate than the TV. And you can see it's changing the colors in the middle of the line. That's what's going on here. This is just randomly changing the background color. So based on where you are in the cycle, it's changing the color on the line. At least when I added this, now you can see the lines are really solid colors all the way along. Because I'm setting the background color, and I'm saying, I'm done, you just draw your line, and then come back to me at the other end. So the other two things, STX, remember I mentioned an X register. So STX is just like STA, except you write to the X register. And DEX is decrement X register. So all that happens when I do DEX is it's subtracting 1 from the X register. So the X register starts at 0 because we haven't done anything. So it's going to write the background color 0. It's going to go down by 1, which wraps it down to 254. It's going to write 254, goes down 253, and it cycles around because there's no, when you overflow or underflow in 6502, it wraps the byte around. All right. But so this is what the fundamentally most difficult thing. Now I'll say that this wasn't so weird back then because this is still remembering the era of drum memory or mercury resonance memory, where even your memory systems were all around timing. So programmers back then were used to timing. It was a big part of what you did. But it's what makes it the most challenging. And it also means you have these infuriating bugs where I have a little thing here where if I bump a wall and hit a collision, something goes wrong with the timing, which means it skips a line, so the whole screen just moves up every time I bump something, just because things are out of sync. So, all right, let's try and do a smooth background color cycle. I think by this point you'll also notice the title of my talk is a bit in jest because you can write Atari 2600 games, and this is how to do it, but it's probably a bit more than even coming to a game jam at Fire Up Unity. There's a lot of stuff you have to learn along the way. I'll also note there's a language called Atari Basic, which is kind of a compiled language that you can use to do some simpler stuff. Okay, so what do we got here? So remember how that previous one was cycling? The reason it was cycling is if you remember my earlier chart, we had the VSync and we had the overflow and the underflow. It was just wrapping around. So at the start of this, what we do is we use these new signals, V blank and VSync. And these just tell it, okay, you're at the top of the screen, this is where you should be, turn off the beam, do your thing. And then we draw 3 lines of that. Now, if you remember that I mentioned the number 37, so now we just loop through 37 lines here to get to the first drawing line. And this is important too, because if you're used to a modern language, a loop would be like for x equals 1 to 10. What we have to do here is we load 37 into our register, we draw a line, we decrement it. And this BNE stands for branch if not equal, which actually means if the register is greater than 0. So what's happening is that as long as it's greater than 0, it goes back to blank loop. So all this thing here is just killing 37 lines. Then we'll actually draw our code here. This is our 192 lines of loop because that's how many, I mentioned 192 lines at one point, but that's how much actual drawing space we have. Then we go back, this is the overscan, and now we've hit our number. And if you don't put the W-syncs in the right place, you get any of this wrong, all of a sudden your whole game is kind of be like scrolling around the screen because you have all the timings wrong. And it's really easy to just do that by accident. And it's one of the more frustrating parts of this process. Okay, so we have this. We have our V blank. We have our scan lines to talk through all that, have our overscan. All right, so let's do a color cycle. So what I'm going to put here is, in the insert code, we will do DEY. Can anyone guess what DEY does? Anyone guess?
Decay or delay?
Decrease the Y register.
Close enough.
STY, color VK, I think everyone now, there we go. So, now we have a nice cycling color. So why is this cycling nicely while the last one was doing that scroll? Well, it's doing that because if you look at my code here, this is every time we draw the screen, we're only going through this loop once. That's what all this other rigmarole is. So we start, we change the background color, we do a whole cycle, we come back to the top. Now we're doing this. The point is the background color is staying the same through the whole cycle. So you can see when we were changing the background color essentially at random, we got all those crazy short chunks. When we change it per line, we got whole lines. When we're cycling the background color in sequence, now we get a cycling background color. The reason I'm showing this is because, again, that kind of sequencing is really key to building stuff on the 2600. All right. So if we wanted to do it slower, we can do some variables here. Copy over exercise 4. All right. So exercise 4 here. So up here, you're going to have variables. So I did say variables are hard, but you can declare variables. That's why assembly is better than machine language. So we can do background color, byte, and cycle speed is the byte. And I was joking about this earlier, but you do sort of have variable types, and then you can do bytes and words and arrays. The thing is, when you do this, it's not all it's doing is the assembler itself keeps a list of your free memory, those 128 bytes you have. Because the first one it sees is like, okay, so they want a byte, so 0, 0 is now going to be referred to by background color, and 0, 1 is going to be cycle speed. So it's not quite like a variable in a modern system. It's literally just a reminder of where this thing is in memory. Okay, so next up, let's go to our code, and we'll show this in sec. So we're going to LDA number 10, we've 10 to the accumulator, STA cycle speed, that's going to store our number 10 in our cycle speed. K, that's a new one. That means Paige Taylor Swift. Transfer accumulator to Y. So that's saying take the number in our accumulator and put it in the Y register, then load 40 into the accumulator and store it in background color. So this is basically, this is just initialization code. Okay. So LDA 10, cycle speed, T, LDA 40, background color. Okay. And, all right, let's do our loop. So, day, BNE, skip, decrement color, LDY, background color, DEY, STY, background color, LDY, cycle speed, skip, decrement color, LDA, background color, and stop calling you oops. Okay. All right. Oh, and I misspelled background color.
Yeah, both cycle speed.
There we go. All right. That's that. And I think, should my variables be somewhere else? Okay. So I'm going to now copy over final version of this exercise so we can show it working. All right. Let's go to the finish version. Oh, I did the finish version. Exercises completed. Exercise 4. There we go. Okay. So now you can see it's cycling slowly, and if we go in here, we could change some of these variables if we wanted. So if we wanted it to go faster, change the cycle speed. Make it slower, it goes up, change it faster to 5. Now it goes faster, we can change a different starting background color. So, very simple. That's how you do loops, that's how you set variables. You can see like 6502 or all this stuff is a weird blend of like really tedious and also terse. So like, it's not particularly verbose in terms of things being long, things are short. But even just incredibly trivial things like small loops, you have to do code. When you do a lot of this stuff, you start writing macros and stuff like you might see like with a template to repeat code. So we're starting to run a little towards the end of the time. So just want to show you a few more things. So I showed you these experiments here. And this is actually no. So if you look here, you can see that the background color transition, even though we're just decrementing by 1 each time, isn't particularly smooth in terms of colors. That's just a feature of how the color charts work on Atari. So if we copy this, the colors aren't like a super smooth, they aren't like a super smooth gradient. Basically, the low and the high values give you a grid like that. So that's why I colored doing this weird kind of cycle. And again, that's what's weird about programming to systems. It's not like you have a 0 through 255, nice and smooth. You have to look at a color chart to even see what you want. All right, so let's get to, so after all that, you know how to set the background color. But obviously we need a little more to set the background color. So let's get to the second most exciting thing we can do, which is the play field. If you look, oh, yeah, that's not right. I think I might overheated. There we go. So if you see that background there, those lines, the Atari 2600 was basically made to make Pong or games like this. So they tried to make the cheapest hardware possible to do that. So you have two sprites. You can see two sprites there. You have missile objects. You have a missile object for each one. And then you have this thing called the play field, which is what's drawing those lines. And the play field is set up with these big blocks, and it can be mirrored or not mirrored. And let's see what we can do with that. All right, so now we're on exercise 5. Copy that over. Here's our play field exercise. We're going to put 2 blocks here. 3 blocks. So here we have LDA, FF. So what's special on FF? FF is 255, which is the same as 1111, 11111, 1111, solid block. So now we're going to stop PF0, stop PF1, stop PF2. These are the play field registers. There's 3 play field registers, 2 or 3. Now we're not seeing anything yet, and that's because we don't have a color set for it yet. So that looks pretty much exactly like what we had for background color, right? But the difference here is that this is actually drawing this with the play field. So if I went here, for instance, and did this, now it's changed because it's loading this 1111, 1111000 pattern. Or if I did 11, it looks kind of like that. Because these 3 play field registers are not all the same size, they're different sizes. But let's go back to having a nice full screen here. So in block 2 here, we're going to load a 0, which is 0, and then stop PF0, stop PF1, stop PF2. Okay, so great. Now we have a line, and you can see it has a certain thickness. That's because you look here, we drew 10 lines before we got here and cleared it. So that's 10 vertical lines of height of the play field. And then finally, let's put something at the bottom. So we're just going to basically do the exact same code up here. So without the loss. So there, we just drew a play field. And again, the reason I'm showing this is one, because play fields actually are like in Atari games that show scores, those scores, that's actually play field graphics. That's not a sprite. That's just turning the play field on and off at the right time. But again, you can see timing is everything, because the way we draw this is we say, I want all the play fields on, count to 10, I want them off. Count to whatever we're counting to there, count to 172, turn it back on. That's how you position things on screen. You're just timing where you want the things to be. So there's an exercise here where we add sides, but that's boring. But since we're getting to the end, I'm going to show you the last thing of note that you can add, which are sprites. And I know you're like, okay, finally sprites. Now we can do something really exciting. Well, you can, but so this exercise contains the side play fields that we added to. So let's draw a sprite. So up in block 1 here, let me do this. So LDA $32 stop hold U G0 LDA stop U0. Wow. Okay, so now we've drawn a sprite graphic, and again, the sprites are the 2 players. What's going on here? So this, all a sprite is you have 8 bits. You can't even, the GRP0 is positioning. How do I say where a sprite is horizontally? Well, I count cycles, and I wait, and when I'm at the place I want it to be, I strobe the GRP0, which says draw it here going forward. That actually is in blocks of 15 pixels. If you want to move it precisely within that, you have to do a separate calculation based on like the modular arithmetic of the base 15 to add a modifier. So you can't even position it horizontally easily. And it's just on or off. So you can see we have those lines down the screen. Well, so 3-2 in this case basically is a pattern that looks like that. And because we're not turning it off, it just happily keeps drawing it. All right, so let's try and turn it off. So there's block 1. So the 3-2 is the color, and the AA is group 0. A shows up as 1 0 1 0. So that's just 1 0 1 0 with a color of hexadecimal 32. And so finally, let's turn this off. So we do LDA 0 stop. And now, again, we have 10 bytes, so we have a 10-line high, 8-bit wide sprite. Now you're probably going to ask, well, that looks more lines. Well, so if you want to do, so I'm going to wrap this up now, but if you go through the rest of the exercise and you're curious, it follows through all these things. And so the way you draw this is you have an index table for each line of the sprite, and then you keep the index in that in your X or Y register, and then every time you go a line down, you increment that, and you draw your sprite from the next line. So if you're drawing a multi-line sprite, just every time through, you're just saying, all right, put this index in, put this index in, put this index in. If you wanted something that is wider than 8, well, you could use the 2 sprites and stick them together to get 16. Or you can start doing weird timing stuff. There's also really odd things where, so you can see here the play field is mirrored. So one of the things you can do, the play field is set a bit that mirrors it or doesn't mirror it. That's one thing you can do. You can set these registers that, so once we get to the planes, you can see this. So there's one plane, now there's 3 planes. That's just because there's a bit where you can say, you know what, I want 3 of these. You can have 1, 2, or 3. So at Space Invaders on the Atari 2600, the only way they can get all the sprites there is by going through and turning, carefully toggling the various sprite modes to get 1, 2, or 3 based on what you've killed. So it's kind of nuts. And I think another important point, just before I finish up, is when you think of the way Atari 2600 games look, there's a very distinct line approach. So if we go back to my game pictures here, okay. So look at that. So what do you see there? Well, you see playfield stuff, right? And you see a couple sprites. Look at Battlezone, which is kind of 3D. What do you see? It's all straight lines. Because those straight lines, like changing the playfield for one vertical scan line, that's super easy. That's something you can do. So there's a distinct look there. Look at how the pitfalls level is structured. It's completely straight. It's these horizontal lines that you're working on. ET we won't talk about. But I think, so like in my home group game here, like so the target line there is a playfield, and those sprites, that's only, again, I only have one sprite graphic. It's just you're timing it and turning it on and off at each point. And that's why, going back to that racing the beam, everything you're trying to do is in between those cycles. And also it's worth noting that you only have, I think you have like, each clock cycle, each color cycle is like, or it's 3 clock cycles per color cycle. So when you're working with a CPU like this, when your chip is like 1.5 megahertz or whatever, what that means is, it's cycling 1.5 million times a second, whatever it is. But these different instructions take different amounts of time. So you see these numbers down here? These are the cycles it takes. So like a stop takes 3 cycles. Dex takes 2 cycles. This takes 2 cycles. So just this loop here has used 9 cycles. And you have like 40 before it starts to draw. So you don't have much memory, you don't have much space on your cartridge, and you have like almost no time to do anything you want to do without kind of stitching it real time with what's going on. All right, so I'm now finished this sequence just to finish up. Go back to players, also that's sprites, so I can do that. I can build sprites. Okay, so you probably have questions coming out of this. How would you randomize it? Well, look up the math on pseudo-random number generators. How can I save a game? Nope. How can I draw a shape? Good luck. Text, well, you do it yourself with playfield graphics. Text is actually kind of one of the easier ones. Floating point math, good luck. Ray tracing, And again, that's what's kind of fascinating about this, because like if you have a 6502 running at this clock speed, I mean you can do like basic wireframe 3D in theory, right? But there aren't many 3D algorithms that don't have you dumping either like vectors or something in a frame buffer. I mean that's what they're all about. Like you don't have a frame buffer, so you can't do anything like that. Okay, what have you learned today? So you've learned a bunch of instructions. You've learned load to accumulator, store to accumulator, load and store from the other X and Y, transfer, accumulator to and from. You've learned Dex and D, EY, and you've learned a branch instruction. And the truth is, with these things, you kind of have all the assembly you need to start messing around with a tool like this, because it's all the same kind of concepts. Like branch is not equal. I mean, there's like 6 or 7 branch instructions, but they're all just different variants of that. And there's subtract instead of add. There's a few other like things, but most of these are just variants on what you're moving to where and how, and what the cycle time is, and what the addressing mode is. You know the bits and pieces of how to program 6502. You're taking numbers, you're sticking them into addresses, you're pulling them from addresses. That's it. And if you get into it, one of the fun things to do is go on like Amazon or a used bookstore and get an old 6502 book, because back in the day, I was joking about floating point, but like people had to do floating point math in assembly because that's how you were writing stuff. So there are books that are just basically, hey, here's 6502 recipes. You can find them online. So you can find all the stuff you need to do this. Now, what can you do with this? So you made 2600 games. You could make Atari 400, 800 games. You have the stuff to start making an NES game. Make an Apple II game in assembly. You could make C64 or Panoramic 20 games. You can make Atari Lynx games. That's kind of, those are one of the other 602. Or you could start the process of learning x86. Obviously, assembly language right now isn't like super important, but it's interesting, it's useful for debugging, it's useful to know how your systems work, and it's kind of fun. All right, so credits. I learned this from a book called Making Games for Atari 2600 by Stephen Hogg. It also uses the 8-bit thing. Book Racing the Beam is just about the Atari, really fascinating. I highly recommend it. The Stella guide was the original how to program the Atari 2600 guide, which got leaked and scanned to a PDF and then refactored. I'm sure it's 100% legal. But that's where a lot of this stuff comes from. There's reference guides. If you're messing around with the Stella emulator, it's pretty good. AtariH.com is like the big site, and that's where you can get homebrew carts and stuff. And then there's a couple other tools there with like a sprite maker and a color charts, and just to show what, if you go through the entire workshop, what you build. So the end result will be this. So I have all of them on here, but let's go to 14. So this is the final thing you'll build, which is just something. You can hear that Ataris have 2 channels of sound. You can do the joystick, you can do the sprites. This originally was going to be the BGS logo. I managed the 4 buttons, and then we've got a challenge. But if you go through this is basically what you'll build. And once you've done this, you've got playfield graphics, you've got sprites, you've got joystick control, you've got that kind of toggling, you've got different sound stuff, and so you have all the bits and pieces to do this more. And if you do get into a lot, I would recommend downloading Stella, learning how to set up the DASM toolchain, because it's a lot easier working with a proper debugger in Stella. And once you use the toolchain, it will also do things like compile in your labels, so when you're walking through the debugger and seeing where it is, it'll say, oh, I'm at this point, instead of just trying to read the assembly language. Okay, so that is my talk. Oh, sorry, last thing. If you enjoy assembly, well, you should play this anyway, but the Zachtronic games, he has a whole bunch of games about various mechanical electronics. TS100, Shenzhen, IO, and Exapunks. All of those are games where you use assembly variants in different ways to beat them. It's kind of semi-fake assembly. TS180 is like a parallel process fake computer. It's really neat. Shenzhen IO also has an electronics component where you have to hook up different components. In Exapunks, you're building viruses that have to go on networks and do things. I would seriously recommend playing one of these because they're all about timing and you're trying to minimize cycle counts, all the things that you really have to do. Like the game I'm building right now, the rhythm game, what's probably going to happen is I hit a point where it works, but I'm just literally out of cycles. There's literally no more room for me to do what I want to do. And now I have to go back and refactor it and figure out how to start shaving a cycle here, a cycle there, so I can do like the one thing I want to do. And these games are really good at training that. Any questions before we go to the next phase? Yes, Jim.
When you pulled up the flash card, that menu seemed like it had more advanced graphics than the console's capable of. How did that work? Or am I just seeing things?
Well, so this is an interesting thing what I said about the retro stuff. Programming for the Atari 2600 now is not like programming for it in 1980, because you have the internet, and you have this community of people pushing the boundaries, and you have like various tool chains you can use to do things. So a lot of the modern games look way better than the older games, because like back then, like Pac-Man or E.T. is one guy, and they're like, hey, we need Pac-Man, have it in a month. And he would just lock himself in a room with a dev box and try and figure it out. You know, now there's all this experience in the community. And I think that's just always important to remember with the nostalgia is it's not really like doing these things back then because you have a community you could work with. But the upside of that is you can do these really interesting things that you couldn't do back then. There's also experiments where people are like trying to, could you make the car like do interesting things like change the memory in weird ways while you're doing it to like mess with the console, stuff like that. Someone else had a question? I thought. No? Dale, did you have a question? Nope. Okay. Mark?
I actually got one. So you're saying that you can't have save points on it, which I understand. Would you be able to program something in terms of like passwords, kind of like how they used to do in Nintendo with like Metroid and stuff like that, or does that take up so much memory functionality?
So, yes, but the thing is, what is your password actually doing? So like if we go back to Pitfall, the way Pitfall works is you basically wrote a system that generates like bytes or 2 bytes, I don't remember, each of which indicates things like, okay, is there 1, 2, or 3 scorpions down below, this, that, or the other. And then you ran it through a bunch of iterations until it spat out a game that is interesting, because there's no room to store all that information on the card. So you could do a password system, but it has to be pretty simple because it has to go to whatever algorithm you're doing to generate your content in the first place.
Do you think it could randomly generate, like the way that it would randomly generate the tiles and it would sync up together, possibly?
So what's funny is there's no way to randomly seed
All right.
because there's no clock.
Got it.
So I'm sure there's like tricks where you can read random memory on it, but like that's the kind of weird thing, like it doesn't have a clock. There's no save state at any time. There's a timer, you can set timers, but there's no clock. So even things like, well, you pseudo random generator and then I pull in this, you don't have that. Like the best you can do again is just like pick random memory locations. It's just so insanely limited, it's kind of hard to comprehend.
Mm-hmm.
Like, my watch can draw to the screen. I mean, I guess it's better than like an old Casio 7 segment, but do you remember the old, like, the game, like you had those, like the calculator watch, you know what I'm saying? Like the cool kid had it, you're like, wow, that's a great watch. That's more powerful.
Yeah, that's what I was thinking.
Yeah.
Do you know if the PAL variants of this could do more cycles because of the difference in scan line and overscan counts?
They are different. I actually have PAL versions on that. I don't know if it's more. I want to say no, like that because they didn't change the clock speed or something, but I honestly don't remember. But it is different. I think I know with other consoles that was an issue where like some ports they had to change because it was.
That's the thing with like the Commodore 64.
Yes.
Because you have like, I don't know, 12 extra lines.
Right.
To run processes on refreshing the screen effectively. You can do the same amount of stuff.
Well, and since you were talking about the cycles, so like this is a little maze demo I put together, and one of the things you'll see is like, okay, well the maze is not mirrored, right? It's not the same on both sides. So this is all playfield graphics, but going to the race and the beam thing, the way this works is like a very careful timing where, so if this is like playfield 0, this is playfield 1, playfield 2, I'm having to copy while it starts drawing this, I have to start getting ready to have this one drawn and then to change the next one by the time it gets there. And I have to do it while it's drawing because if I do it ahead of time, it's just going to mirror this thing. So to get an asynchronous maze like this, to get an asymmetrical maze like this, you literally have to time all of your things perfectly. So you're changing these playfield graphics registers while you're drawing to flip it over. And this is the case, Mark, where like this maze, I actually wrote a Perl script or Python script that generates the maze as binary data, and then I just put like a bunch of them in you could rotate. But even simple things like drawing a maze, you just don't want to draw a line. You just can't.
I think that was interesting signal tone saying asynchronous, because
Yeah.
everything is so timing based that it's actually kind of right.
Yes. Well, and it's the way that like, I was joking about the 60 frames a second, but it is kind of funny because like, again, there's modern hardware that can't render 60 frames a second, but there's literally no way to render any speed other than 60 frames a second because that's what it's doing. and you're not rendering anything. You're just like fiddling with the registers in the system. It's just like happily turning on chunks of graphics or turning them off. And so that's the other like weird way, really the thing we have to think about.